Hi, so let's spend a little bit talking about a kind of classic problem where we have two objects that are in contact. This is sort of the basic version of questions that you'll see a lot where you have things that are connected together and we want to understand the forces going on in between them. So the setup is basically the following. You have two blocks, say, that are in contact. You're pushing on them with a force from the left there, so it's pushing to the right along the x-axis. And the two blocks, M1 and M2, so M1 is then pushing against M2. And the question that we're interested in is what does the force look like between them? So the force of M1 on M2, or we could also think about it as the force of M2 on M1. So let's start by making some free body diagrams for each of these blocks. So for M1, we have the force that's applied to it, of course. We would also have M1G, its weight, and then we would also have the normal force pointing perpendicular to the surface that they're resting on. And the last thing that we would have in here is the force of block 2 on block 1. So pushing in the opposite direction there. For M2, pretty similar story. We would have M2G, its weight pointing down, the normal force pointing up, and then additionally we would have, the force of 1 on 2 pointing to the right. And now we kind of have our accounting of all the forces that are going on these two objects. So we can then turn to Newton's second law and see how they would move. So, and notice we have kind of three things that we can look at. Since these objects are moving together, we can point out that the sum of the forces, so specifically we're concerned about x because the system is not accelerating in y, but the sum of the forces in x is F, and we know that that's going to equal the mass of the system times the acceleration. The mass of the system is the mass of both of these added together times the acceleration. So, and then let's look at each block individually. So for mass 1, if we look at the sum of the forces in the x direction for mass 1, we have F minus F2 on 1, since it's pointed, in the negative, along the negative x-axis. That's going to equal mass 1 times its acceleration. I'll also here just take a second. Let's just sum the forces in y just to see what it would look like. So this would be, the normal force pointing up minus m1g. That would in general equal mass 1 times acceleration in the y direction. This is implicitly in the x direction. But this is 0 because the object is resting on the surface. So from this, you could make statements like the fact that the normal force is equal to the weight in this situation. But this is of less importance to the question of, what are the forces in between these two blocks. But we'll have that there for you as an example on mass 1. And then let's look at the forces in X on our last block, M2. So we would have F1 on 2. That's going to equal mass 2 times the acceleration. So we basically have 3 equations. Let me just indicate these. Three equations that we can make use of. So the first thing is, it is pretty simple for us to pick out the acceleration of the whole system. So if I, here, we'll do from equation 1, notice you'd have you could solve this for the acceleration, the force over the sum of the masses. Okay. Now, we have two other expressions, equation 2 and equation 3 here. Equation 3 is actually pretty simple. Let's substitute equation 1, or our result here for the acceleration, into equation 3. So let's see here. So when we do that, notice we have F1 on 2 equals M2A. So this is going to equal M2 times F2. So this is F1 on 2. And notice this kind of agrees with our intuition. The force of 1 on 2, as M2 gets really small, that force is going to go to 0. So in other words, it's not going to require any force to accelerate mass 2 if mass 2 doesn't have any mass. Okay. So, and this is close to, this is one sort of half of what we're looking at. Let's also sub into equation 2. So this will be slightly more complicated, but we see that F minus F2 on 1 equals M1A. So when we substitute this in, we would have, here, let me, so our acceleration again is F over M1 plus M2. We can solve this for F2 on 1. So what would that be? We would have actually F minus M1F for M1 plus 2. We can multiply, so notice we don't have a common denominator here. We can multiply F by M1 over M2. So if we do that, here I'll be real explicit about this. So they now have a common denominator. And if we do that, notice we have an M1F minus an M1F, so these would cancel. And then you can see what we'd be left with here would be F 2 on 1 equals m2f over m1 plus m2. So the same thing. Now, there's one important thing to point out about this. F1 on 2 is pointing to the right. So in other words, this is in the positive I hat. F2 on 1, however, although it's the same size, you can tell it's pointed to the left, i.e. the negative I hat. Just for completeness here, this would be the positive I hat. So these forces are the same size, but in opposite directions. And this is what we would expect based on Newton's third law. If one object is pushing on the other, F1 on 2 say, the object will push back on the first with a force that is equal in magnitude but opposite in direction.